On Wednesday, OpenAI announced something that sounds almost impossible. Its latest version of ChatGPT had solved an 80-year-old problem in discrete geometry, a problem described as one of the most important in combinatorics and one of Paul Erdős's favorite questions. The problem itself is beautifully simple to state. Imagine placing endpoints on a plane. Now ask how many pairs of those points can be exactly 1 unit apart. That's the planar unit distance problem, first proposed by Erdős in 1946. For nearly 8 decades, mathematicians have chipped away at it, tested constructions, chased boundaries, and wondered whether the familiar square grid arrangement was essentially the best way to maximize those unit distance pairs. And now, OpenAI says an internal reasoning model has disproved that long-standing expectation. The model produced an infinite family of examples that improves on the classic square grid construction, and the proof has since been checked by external mathematicians. What makes this result especially striking is not only the mathematics, but how it was found. This was not a specialized geometry engine or a system that was carefully built to attack just one problem. It was a general-purpose reasoning model tested on a collection of Erdős models, and it appears to have contributed to some genuine results at the frontier of mathematics. Now, what exactly happened here? Did AI do math in the way that mathematicians do math? What does it mean to solve a famous open problem? And what are the consequences of research proof, creativity, and the future of the mathematical profession? Now, to help us unpack all of this, we brought in Daniel Litt, a professor at the University of Toronto who was involved in the OpenAI project. Today, we're talking about how unit distances, Erdős, discrete geometry, AI reasoning, and whether this moment marks a new chapter in how mathematics gets done. So, I'm your host, Autumn Fnaf. I'm joined by my co-host, Noah John Syracusa, and this is Breaking Math.
Let's start by having you share with us, what was this conjecture? Before we get to the solution, what was this Erdős problem?
Yeah, so let me start by introducing the question. So it's kind of a basic question in discrete geometry, as I understand it. It's this: so you put a bunch of points in the plane, so a two-dimensional configuration of points, and you want to arrange it so that as many as possible of them are exactly distance 1 apart. So maybe the thing you're interested in is like what fraction of the total number of points are exactly distance 1 apart. So Erdős observed that if you take just a grid of points and you rescale it appropriately, you can get a pretty good construction as you increase the size of the grid and scale appropriately. And he conjectured that asymptotically, this is the best possible. So as you get more and more points, the best you can do is just put a grid in the plane. So that was the conjecture. There was a known kind of upper bound on how well you could do, which was a bit worse, a bit better than what Erdős constructed. And a lot of effort was put into improving that upper bound, so trying to get it to match Erdős's construction under the belief that this construction was in fact best possible. And the new result, in fact, it wasn't. So there's now a better asymptotic construction produced more or less autonomously by an internal model at OpenAI.
So this isn't related to sphere packing, but I think it had been known for a while what the optimal among lattice packings, so packings that really are more grid-like you're mentioning the other conjecture, that just kind of repeat the same way. We kind of knew what the best one of these grid-like packings is, but it's very, very, very hard, in fact, Fields medal worthy, to prove that there was no better packing if you break this grid pattern and are not a lattice. So I think this is kind of interesting. In this other conjecture, what OpenAI, their chatbot, found is, yeah, there is actually a better solution to this conjecture if you leave the grid world and you enter this more chaotic or fractal-like.
That's true, but I think one should actually also think of the new construction as being kind of grid-like in some way. So it's still construction using algebraic number theory. You can think of the grid as being about the Gaussian integers, so z adjoin a square root of -1. And the main idea of the construction is to replace that number system with a more complicated one, or a tower of more complicated ones. So in some sense, actually, what you get is still looks pretty grid-like.
Okay.
Maybe, a shifted grid or some kind of collection of grids on top of each other. Yeah, but yeah, so it's I think there's we still don't actually know what the best construction is. So I actually think there's kind of an interesting question: is like, are the best constructions algebraic in this manner?
I see. So that they found a more interesting way to set up a grid that beats the previous one, but we don't know if more
Yeah, we still
progress
don't
is
know what the
possible.
best is, yeah.
So I know we have a lot of folks who are at various levels mathematically. In this case, what does this construction more look like, especially when we're talking about it being on a square grid or packing spheres? And we have to look at things that are essentially optimal. What is that looking like for folks?
Yeah, so maybe I can say a little bit about Erdős's original construction, and then
Sure.
kind of I think once one understands something about that, it's pretty natural. Like in retrospect, the model's construction is kind of natural. Okay, so why is a grid a good idea? So like, what does it mean to find a bunch of points that are distance alpha apart? Right. What it means is that you can write alpha squared as a sum of two squares, right? Just because the square of the distance between 2 points is, by the Pythagorean theorem, the square of the horizontal distance between them plus the square of the vertical distance between them. So a grid achieves, let's say, the distance square root n a lot if n can be written as a sum of two squares in many ways. And this is a sort of natural number theoretic question that we know a lot about. Like, basically, n can be written as a sum of two squares in many ways if it has a lot of prime factors. Well, really, if its square free part is a product of many primes, which are 1 mod 4. Already you can see some number theory happening there, right? So what you do is you take a big grid, you find an n which can be written as a sum of squares in many ways, and then you rescale it by 1 over root n. So that's Erdős's construction. Now, maybe the observation here, which is kind of very well known to number theorists, is that this fact about writing numbers as a sum of two squares in many ways is related to something called splitting of primes in the Gaussian integers. So you want to understand primes where -1 is a square mod p. And once you say that, well, you can just replace the Gaussian integers with some other ring. And the model's idea is like to think about what kind of other rings inside of the complex numbers give you the right behavior. And what I realized is that there was something sort of already in the literature which works well, called a class field tower. So these were discovered by Golod Shafarevich in the 60s. That realization is not obvious. I think it's the main kind of clever observation in the proof. But the actual construction of these towers of number systems, number fields, goes back to the 60s. So really, what the model kind of observed is that by sort of generalizing Erdős's original construction, you can do it a lot better.
So to put that in simple terms, it sounds like originally this is a geometry conjecture, but it very naturally translates into very basic number theory, right? Squares and sums and things.
Yeah.
And essentially what the model did was found much fancier number theory that could kind of get more mileage out of that translation from geometry to number theory.
That's basically right. Yeah. Yeah. I mean, I wonder, I think, it is true the number theory is very fancy, but it is pretty classical. It's something I think you would expect most algebraic number theorists to be familiar with.
All right, fancy for us mortals, ordinary
Yes.
for professional number theorists. So that's the setup. That's more or less where things were left with Erdős. 80 years passes. People mostly, it seems, thought that his conjecture was true. OpenAI's system seemed equally willing to explore it being true or false, and it ended up finding a false, a counterexample.
That's right.
Do you think if humans had really given false a chance and pursued that?
I'm sure people tried to come up with counterexamples. I think this is a big accomplishment. I don't want to downplay it. And I think this kind of judgment is very, very hard to do in retrospect. It is the case that sometimes people just miss, kind of clever, beautiful constructions like this. I think it's plausible. Like, if you'd gotten the right people in a room and said, like, you have to work on this, like, maybe people would have found it. Like, probably, I guess. I think there's a lot of like open questions where if you have a Manhattan Project devoted to it, they're going to be solved in a month or two. But one of the amazing strengths of the models is they have a lot of attention. You don't need a Manhattan Project to focus, experts on it. You can just like throw 1,000 problems at them, and sometimes they'll find an answer.
And that kind of moves us to, I think, where we want to center the discussion, which is the bigger picture. We're interested in the specific problem, but we're also not. We're interested in the larger conversation. And what we're trying to figure out, I would say, as a mathematical community, us as experts, our audience, everyone, is what's the significance of this finding?
Yeah.
And I think one of the things we're realizing is, okay, it's not so much if AI is smarter than humans and could do things that we couldn't. As you're saying, we probably could have done this anyway if we were sufficiently incentivized, the right people, the right amount of time, it would have happened. So it's not that this was some breakthrough like Riemann hypothesis that we were just nowhere close to, but it's also so even if it is something that's kind of within the human reach, the fact that a single prompt can do what would have taken a lot of concentrated human effort. And I think what helps me understand the profundity of this is, okay, to get, a Daniel Litt and other experts in a room, there's only so many of you. You only have so much time. That's a very limited resource. But once we have AI systems that with a single prompt can start solving serious math problems, what's stopping us from, running a million of these things across millions of problems? So share some thoughts in this direction, scaling up mathematical progress now that AI is at this level.
Sure. Yeah. I mean, okay. So first of all, I do think this is a big deal. Like, I really don't want to downplay it. It is in some sense the argument is recombinatory. A lot of math has that flavor. Like, I really don't want to give the impression that this is not a big deal. This is something people really care about.
But I hear a but coming.
No, there's no but. No, that and.
Right. We'll take that.
And I mean, yeah. So as you say, like the way the models do math is very different. Like productively is very different from how human experts do math. Right. So right now, the productive way to get math out of the models is you throw 1,000 problems at them, and they solve some portion of them, and then some much smaller portion of that will be really interesting things that people care about. The way a person does math is like maybe they're driven by their personal curiosity and they study a question or sub questions quite deeply and like develop some understanding of that and hopefully make some progress. The models can help with that too, but my sense is that like they help less. Like, and why is that? Well, like different people have different strengths, and also the models have some different strengths. Like my sense is that like okay, even in the areas where they're strongest, like the models definitely don't like strictly dominate human mathematicians. They have strengths, like for example, they're very patient, they have very broad knowledge. Um, but there are definitely mathematical tasks, typically like less verifiable ones, that they're much weaker at than human mathematicians, I think. I'm not making a prediction about the future, just describing the current status of things. And of course, where the models are making progress is where they're strong. We maybe don't know where that is in advance, and I think that's like partly why you like throw 1,000 problems at them and you see what they pick off. The main strength they have is they don't get tired and they have like a more or less unlimited amount of attention. So you really can, you can't have a human try 1,000 problems one after another. Not in a meaningful way. I mean, I think there's like another axis of this, which is like economics. So I think it's fair to characterize this result as like an Annals paper. Like, so Annals is arguably the best journal in mathematics, or one of the top 5 journals in mathematics. I think probably this paper would be were it to be submitted to such a journal, it would be published there or an equivalent place. You can ask how much does it cost to get a human to produce an Annals paper? And I think maybe a guesstimate is something like $100,000. Like if you count training of a person and their, how much mathematicians get paid per year. I think you can ask, like, what was the cost of getting the model to producing this result? My guess is the marginal cost was on the order of a couple $1,000s. In the sense that, like, if you just ask how much did like this one run cost, it was that much. So probably somewhere between $100,000 and $10,000 seems, just based on the chain of thought, seems like a guess. My guess is on the lower end of that, so like probably under 1,000. And this is really just a guesstimate, so don't take this as too meaningful. Of course, this was like one run of probably hundreds or thousands, so probably that probably some of which other ones were solved and are not Annals papers. But it seems plausible to me that like the marginal cost of producing this, if you count all that stuff, was like pretty comparable to getting a human to produce an Annals paper, probably lower. Right. So that is some way of measuring human capacity as opposed to model capacity. I think it's misleading in a bunch of ways. So, for example, like the kinds of papers I produce are very, very different. from this kind of paper. So if you say like, okay, well now the models can substitute for human mathematics at like about the same cost, like I think that's not accurate because they're substituting from some for some tiny portion of human mathematics. But yeah, I think there is an argument to be made like that. The economics at least of producing this mathematics autonomously is like now not that different from getting humans to produce some mathematics.
Now, that actually makes me wonder a little bit more about should AI generated proofs be held to different standards than actually human generated proofs? Whether that's in monetization or we can find subtle errors in these AI generated mathematics hard that may even be harder to catch in the long run.
Uh, yeah. So I don't. Should we hold them to different standards? I mean, I think like ultimately no. Like if you view math as I do as like a science, like the only standard is it correct? And I think that's a kind of a okay. I've been in informal mathematical writing. There is some question about that, but like for example, in this case, a lot of mathematicians check the argument, including me. I'm very confident it's correct. I'm probably much more confident about it than like if you chose a random paper on the archive. Like basically just because it's like a 3 or 4 page, pretty simple argument. In the end, and I get very clever, but yeah, not like I've written a 93-page paper. I have no doubt that there are like typos in that. Although I'm quite confident the argument overall is correct. Um, yeah, and I found lots of errors in published papers, even published papers at quite high level. So yeah, I think in general we should have higher standards than we do. Like I think, but yeah, I don't see why at least at the level of correctness, we should have different standards for humans or AI. I think there are some ways that AI writing is different. So one, you alluded to this, it is I think harder to check um, work produced by AI than work produced by a human, um, largely because like the standard of writing is much lower right now. And then also, I think the way they're trained, they're trained full of verifiers, so they produce kind of very plausible looking text that is not necessarily correct, but is very plausible. I think that's getting better, actually. So my sense is that the latest models are like pretty reliable, and you can really increase reliability by just saying like, okay, you wrote this, is it correct? And that if it says yes, that like doubles the likelihood it's actually true. Um, yeah. So the other thing is like, we have standards about assigning credit and fairly, like tracing like the intellectual lineage of a method or idea. And there, the AIs are at present way worse than people. So for example, this construction, the unit distance problem used something called a class field tower. I alluded to this, and in particular, it used a slight twist on the original Golod-Shafrovich construction, where you need to produce class field towers with many split primes. Okay. Whatever that means. So this is something that was done a few years ago by Hajir and Ramakrishna, and if you look at the chain of thought, which OpenAI made public, the model specifically mentioned, so like this can be done using a technique of Jeremiah and Ramakrishna, and then in the final write-up it produced, that's nowhere to be found. And there's other ideas in the proof that are maybe due to Ellenberg Venkatesh or other mathematicians. Like there's a sort of a number of techniques that appear, and that like to an expert you can kind of trace their intellectual lineage, but like the AI write-up sort of wanders that in some way. So the humans, including me, produced it sort of more digested write-up where we tried to like discuss those that intellectual history of the argument, and some of that can be extracted from the chain of thought, but some of it is really not clear. So yeah, I mean, of course, humans are not perfect at assigning credit either. There's like lots of if you ask an academic like do people cite me appropriately? I think you're about to have a pretty pretty rough conversation in general. But you know, uh, uh, there is some question there about like how to write in a way that like you know uh, accurately gives credit. From the point of view of doing good science, like there is a question of like how important that is. But of course, like the development of human capital and like institutions that currently exist, like assignment of credit is pretty important.
Now, what about, let's think for a second about the kind of larger corporate portrait here. Basically, I want to ask, why do you think OpenAI is interested, and I think Google and others are interested in solving math problems? I could see some potential answers. One, just to see how smart their AIs are, right? Once it's able to do math problems, everyone thinks math is hard, and to be good at math, you have to be smart. So one is just to sort of benchmark intelligence. One is
Yeah.
that there is actual economic value that, they're trying to build the next Einstein. And once you have Einsteins, you have a lot of innovation. I
Did
could see another being
Einstein
sort
have
of press
economic
release.
value?
Like it's an easy way to brag that we're winning the AI race if our models are solving harder problems than your models. So, but I'm curious, what's your take?
Yeah, so I think the factors you mentioned are part of it. Like certainly, like I think the C-suite of these companies probably mostly cares about PR. Um, from the point of view of actually training the models, my understanding is that like it's been a general pattern that training techniques that help the models do well on math generalize. So, for example, that Amy was a middle school or high school math contest that was sort of one of the earlier math benchmarks, and the methods that were used to saturate that benchmark seem to have like basically broadly generalized to make the model smart in general. And I think that's sort of a general pattern that my understanding from talking to people at the labs is that they feel that making the models better at math helps them develop techniques that generalize to other valuable outputs. Um, I think actually another reason is just like there are a lot of mathematicians employed at the labs and they like math, and so they're trying to do cool math. That's my favorite reason for the frontier labs focusing on this thing. Like there's a lot of I have friends at the labs who are very serious mathematicians, and like I think they're just really excited to do some cool math.
The
That's my favorite reason. I'm a little less, excited about the PR extravaganza and hype machine. Like if a human were to solve the unit distance problem, the way it would be announced is they would post a paper to archive, and they wouldn't have video with stirring background music and stuff. Probably there would be like a quant article about it.
But
Um,
let me zoom in on that last point you're making, that your personal interest in this. I think that's really great, and I just want to amplify one aspect. There's this horrible phrase that we hear in the academic math community whenever someone leaves academia, whether as a grad student or a professor, doesn't matter at any level, we say they're leaving math. And this
yeah,
infuriates me because very often they get a job where they are very much doing math. They did not
right,
leave math, they left academia. So I think
right,
what you're pointing out is this is a great illustration where someone can leave academic math and still do profound research that's
yeah,
the same kind of research we're doing in academia.
for
So it's
sure.
just
I
one
think
more way
one
where you don't have to leave math, just you can leave one employment sector, but you're not leaving math.
Right. Yeah, I mean, like, one cool thing about this is, like, historically, it's been kind of unusual for there to be jobs outside of academia where you can really do fundamental math research. So, like, Bell Labs and Microsoft Research are examples, but, there have not been so many, and now, I think the labs have produced a space for this. I think you're still kind of beholden to commercial interests a little bit more than you are in academia, but yeah, there's definitely cool math happening at
I
those places.
I think that we're actually missing a big point on why they're interested in research. Beyond this, we've got two critical things that hold a lot of our infrastructure together. And it's all based on a lot of post quantum cryptography. So the more that we can solve these algorithmic problems in public and or private, a lot of institutions like NIST, for example, Dr. Dustin Moody is one of the heads of post quantum cryptography at NIST, and they put on hackathons for people to solve the algorithm because we're looking for the next largest prime number or something even larger. So we have a lot of data encryption, everything from our bank structures to just coding up a secure line. That's all on post quantum cryptography. So the fact that we're interested in a lot of math and number theory, it's it's the stuff that we essentially need to have for foundations to be able to better our security. Some of this stuff is not going to be public.
Well, to better our security or to crack the security that's out there, it could go
Yes.
both ways. But
Sure.
that's a
Yeah. I
really
So
mean,
good
I
point.
think at least so far, my sense is that AI tools have not really had a significant impact on those areas. But yeah, I'm sure like all areas of math, eventually they'll be have some kind of impact on
But it
that kind of
does
thing.
I think Autumn's right. Like it absolutely seems like a direction that there is a lot of interest and mindfulness that they might be heading towards.
Sure. Sure.
I mean, we've seen this already on the computer science side, like with Claude's Mythos, Anthropic's Mythos of here's a system that can expose all these vulnerabilities in more computer science sense of like, oh, you're using some open source software that has this vulnerability, no one noticed. And I think Autumn's hinting at a really interesting point here, which is we also a lot of our infrastructure relies on mathematics and number theory.
Sure.
And there may be vulnerabilities there that we haven't uncovered, and
That
AI
would
may
be very
be the one that
interesting.
gets us there.
Yeah.
That's great point.
What's one thing that you want people to know about using AI and technology to improve their mathematical ability and understanding? And what should they be aware of or maybe wary of?
Yeah, I mean, it's a big question. Definitely one thing is just it's a really exciting time right now. Like, I think we're about to see a vast increase in the available attention uh, we have to aim at interesting mathematical problems. So I think we should expect a lot of exciting results in the next few years. I think there's some question as to what that looks like and like how our institutions adapt. Like there are a lot of challenges around training, like both at the undergraduate level. Like now, the models can do any problem set you would reasonably give an undergrad, and so that creates a lot of educational challenges, and also just training, future mathematicians, and I think that it's hard to imagine that. Okay, at least in my view, no matter how strong the models get, we still want to develop human capital in mathematics and make sure that there are people who can understand mathematics. And I think there are real challenges in adapting our current institutions to increasing model capabilities. And so, yeah, my hope is that listeners think about that and think about what kind of human capital in mathematics should look like in the next few years, and how our institutions should adapt to changing technology in the area.
Let me just ask a quick follow-up on that. Do you think that every math student at various levels, undergrad, grad, needs to learn how to use LMs at this point, or could one have a successful career ignoring them entirely?
Well, I think you definitely cannot ignore them. It's definitely if capabilities were to freeze right now exactly where they are, maybe you could. They're not going to freeze. I mean, the models are rapidly getting better, and there's no sign that that's slowing down. Um, as you have to learn to use them. I mean, they're pretty easy to learn. You just, it's like talking to a person. So yeah, I don't think there's some amount of skill involved, and I guess Codex is an app with various menus and so on that one needs to know what the buttons mean. But it's something you can pick up in a few hours. But yeah, I
But it
think
is
people should.
becoming a central part of the toolkit of every
For
working
sure, yeah,
mathematician.
yeah. And I use AI tools all the time, and I think it's yeah, I wouldn't say, you know, in my view, one of the fundamental goals is of mathematics is human understanding. Like, I'm in it because there are certain fundamental questions I want to understand the answers to. Um, and like an LLM or whatever, any kind of technology or another person cannot understand something for you. Like you just have to put in the work. I think there are a lot of ways that LLMs and other technology can help with that, but it's not a substitute. Um, so yeah, I think it's important, but it's not. There are goals in mathematics other than the production of papers. I would argue the production of papers is one of the least important goals in mathematics. Although the production of knowledge and understanding is very important. And selling analyst papers to L'Hopital. Yeah, exactly. Yeah, making cash is the goal of academic mathematics. Yeah, uh, sort of the opposite of the goal of academic. One of the
Well,
most expensive
there's something for
professions.
everyone.
Yeah, yeah. I think being an academic mathematician is one of the most expensive professions you can go into in terms of opportunity cost. Yeah, Anyway, I mean, all I'm saying is I think there's a lot of goals in mathematics, like around producing good science and producing human capital and producing understanding, which are a little bit orthogonal to what the technology is useful for. But yeah, certainly the technology is very useful for many aspects of the profession.
So, what does this tell us to be a mathematician in today's world? The message is quite simple. Learn to use AI to increase productivity as a tool, but you are still of value. We still need to be more clever than machines and validate the work that they're doing. So, until next time, stay informed of the world around you and keep asking questions.